3 major earthquakes struck in less than 30 minutes. First, Venezuela shook. Then it shook again, 40 seconds later, from almost the same place. And before the world had even processed that double hit, Japan's coast started shaking too. Maybe it was coincidence. Maybe it was just another violent day on a restless planet. But there is one reason scientists and earthquake watchers are paying attention now. Because this has happened before. And the last time Venezuela opened the pattern, the shocks did not stay in Venezuela. The Venezuelan earthquakes struck along one of the most active plate boundaries in the Western Hemisphere, where the Caribbean and South American plates grind past each other in opposite directions. South America pushes west. The Caribbean plate slides east. That motion creates what's called a strike-slip fault, and it had been building stress for a long time. The first quake was a 7.2, about 20 kilometers below the surface, deep enough to spread energy across a wide area, but shallow enough to cause serious damage. Then, 40 seconds later, a 7.5. Even shallower, 10 kilometers down. When 2 large earthquakes strike that close together in time, their energy doesn't add neatly, it combines. The seismic waves from the first rupture amplify the motion already underway from the second. The ground displacement is far greater than either quake would have caused alone. Structures that might have survived one rupture came down under both. The destruction was severe. Reports suggest more than 40,000 people unaccounted for. Entire neighborhoods flattened. This was among the most destructive seismic events Venezuela has seen in living memory. But what made scientists look twice wasn't just the scale. It was what they recognized. In 1812, Venezuela was struck by almost exactly the same event. An earthquake doublet, similar magnitudes, along the same fault system. Somewhere between 10 and 30,000 people died. That alone would be a remarkable historical parallel. But what happened around that event is what seismologists are thinking about right now. In 1811 and 1812, centered almost directly on the Venezuela quakes in time, the New Madrid seismic zone, buried beneath the Mississippi River in the middle of the United States, produced a sequence of devastating earthquakes, multiple magnitude 7s and 6s months apart. And after the Venezuelan doublet, 2 more large earthquakes struck Southern California, both magnitude 7 or greater. Scientists don't have 5,000 years of data confirming this pattern repeats reliably. They have one clear historical example. But one example is exactly how patterns get noticed. And right now, that pattern has just replayed its opening scene. Most people assume that once the shaking stops, the energy is spent. That's not how Earth works. When a large earthquake ruptures, it releases 3 types of seismic waves: the fast compressional wave, the slower shear wave, and surface waves, which travel along the crust and carry the most destructive energy for populated areas. But here's what rarely gets discussed. Those surface waves keep going. They circle the globe. They reflect off internal boundaries. They can travel tens of thousands of kilometers and still carry enough energy to matter. The 2011 Tohoku earthquake, magnitude 9.1, generated waves powerful enough to travel all the way down through the mantle, reflect off Earth's outer core, and return to the surface about 16 minutes later. That returning wave moved the Japanese landmass 6 millimeters eastward. Not the initial earthquake, the reflected wave. Think about what that means. A fault ruptures in Japan, and minutes later, the energy bouncing back from nearly 3,000 kilometers underground causes additional measurable ground movement at the surface. Now scale that idea to Venezuela. 150 kilometers of fault rupture, 2 compounding quakes. That energy is now propagating outward across the entire globe, absorbed into rock, loaded into other fault systems, nudging already stressed plate boundaries just a little closer to their own breaking points. Energy is not destroyed, it redistributes. But seismic wave propagation is only part of what scientists are trying to understand. Because right before the Venezuela earthquake struck, something else happened. Something that wasn't underground at all. About 10 days before the Venezuela event, Earth was experiencing what's known as a king tide, one of the strongest tidal maximums in the lunar cycle. When the moon is at its closest approach to Earth, the gravitational pull reaches its peak. And tidal forces don't just move the ocean. The crust itself flexes. The solid ground rises and falls, barely perceptible to anyone standing on it, but measurable with precision instruments. Along a fault already accumulating decades of stress, that cyclic flexing can act as the final push. Research suggests tidal maximums may increase earthquake probability by roughly 0.5% during peak periods. That sounds negligible. But a fault sitting at 99% of its critical stress threshold doesn't need much. The more contested finding involves something much farther away. In the hours before the Venezuela earthquakes, a high-speed stream of solar wind, generated by a large coronal hole on the sun, made contact with Earth's magnetic field. Solar wind velocity climbed to around 600 kilometers per second. At the moment that stream connected with Earth's magnetosphere, both the Venezuelan doublet and the Japanese quake occurred. Scientists are careful about this. The data connecting solar activity to earthquake timing is preliminary. We've only had reliable solar wind observations for about 50 years. The lunar tidal cycle alone runs 18.5 years, which means you'd need a century or more of precise seismic and tidal records just to establish a confident statistical link. But the correlation keeps appearing in the data. Researchers are publishing on it. And this event followed the pattern. We are currently at the end of the most active phase of solar cycle 25, moving into a descending period towards solar minimum. Researchers have observed an inverse relationship between solar activity and volcanic eruptions. As the sun quiets, volcanic output tends to increase. The 2022 Hunga Tonga eruption, one of the most powerful on record, occurred during a relatively quiet solar period. Significant volcanic activity has continued globally into 2025 and 2026. More recently, a 5.7 magnitude earthquake was recorded approximately 50 kilometers directly beneath Mount Fuji. Mount Fuji last erupted in 1707, following a major earthquake. The seismic waves from large ruptures propagate through volcanic plumbing systems, disturbing magma chambers and conduits. That connection is documented. What happens beneath Fuji going forward is one of the things scientists are watching. Off the northern coast of Japan, the situation is more immediate. For months, multiple magnitude 7 earthquakes and dozens of smaller ones have been clustering in a region that includes sections of the subduction zone that didn't fully rupture during the 2011 Tohoku event, and that have since absorbed additional stress from a major Kamchatka megaquake in 2025. Before the Tohoku 9.1 struck, there was a magnitude 7.3 foreshock 2 days earlier. In terms of energy, that foreshock was a fraction of what followed. The question scientists are sitting with right now is the current clustering in northern Japan relieving stress, or is it foreshadowing something larger? There is no clean answer, but the structural conditions for both scenarios exist. Several fault systems around the world carry elevated concern in the current window. Japan's subduction zone, particularly the sections loaded with stress from both the 2011 Tohoku rupture and the 2025 Kamchatka event, remains a priority. Japan is the most seismically active nation on Earth, and sections of the offshore fault have not yet fully released. The San Andreas Fault in California has accumulated stress at some of the highest levels recorded in the historical and geological dataset, according to current strain modeling. It is not a question of whether it ruptures. It is a question of timing and magnitude. The new Madrid seismic zone in the American heartland produced catastrophic earthquakes in 1811 and 1812 in close temporal connection with the Venezuela doublet of that era. That pattern is now on researchers' radar again. Colombia sits adjacent to Venezuela along directly connected fault systems. In 1967, a major Venezuela earthquake was preceded by a magnitude 6.7 in Colombia just 4 months earlier. That precedent doesn't guarantee a repeat, but it's the kind of historical correlation seismologists take seriously. And then there's New Zealand. The Alpine fault has a recurrence interval of roughly 300 years. Its last major rupture was in 1717. By any geological accounting, it is overdue. Scientists don't know the exact timing. They know the fault is ready. Near Trinidad and Tobago, following the Venezuela earthquakes, satellite and ground data indicated approximately 25 feet of coastal uplift along a stretch of shoreline. That kind of surface deformation is significant and, as of current reporting, not fully explained. Scientists are studying it. None of this is a reason to expect the worst. Elevated seismic probability is not a guaranteed outcome. Faults at critical stress can stay locked for years or rupture next week. Nobody can set a calendar date. But if you live anywhere near a known seismic zone, and there are hundreds of millions of people who do, the window after a major global earthquake sequence is the right time to check your preparedness, not ignore it. The basics are straightforward. Know in advance where you'll go if shaking starts. Outside and away from structures if possible. Under a solid table or in a door frame if you're indoors. Protect your head. Don't move until the shaking stops. Modern earthquake alert systems can give you 5 to 15 seconds of advance notice. Enough time to act if you're already thinking about it. These systems work through P-wave detection, the fast, relatively weak compressional wave that arrives slightly before the destructive shear and surface waves. Your phone can receive these alerts. Make sure it's set up. Keep a basic bag near the door. Water, food, a first aid kit, a hand crank or battery radio, an emergency blanket. A small solar panel paired with a portable battery can charge a phone and run a light for days. These aren't dramatic preparations. They're the same things people in Japan treat as ordinary household items. What happened in Venezuela is not just a disaster story. It's a signal from a system that has been sending signals for as long as the crust has moved. Earth's faults don't operate in isolation. They share energy. They respond to tides and solar wind and the accumulated stress of neighboring plates. When one section ruptures after decades of quiet, that rupture doesn't disappear. It travels, it loads, it waits. We can measure the stress. We can map the faults. We can study the patterns going back centuries. What we still cannot do is predict the exact moment, but we know more than we did. And after Venezuela, what scientists know is that the global seismic system is more connected and more active than most people realize. The question isn't whether more large earthquakes will come. The question is where, and whether the people in those places are ready.